Okay, now it is recording. This is our second lecture for 719 Mathematical Economics. And last time we were working on a problem. So let me rewrite the problem here. So this is a very simple master apprentice problem. So there is a production process. In this production process, there is a master, okay, who works to produce something in his or her workshop, okay, and he can also he or she can also hire some apprentices. Okay, so in this problem we have alpha between 0 and 1, a greater than 0, which is exogenously given. So this is a productivity term. K is also exogenously given. This is the capital stock of the workshop. And there is also this wage level, which is also given. All right. In this problem, we normalize price to unity. Okay. So this is a one variable problem, as you see, because there's only one choice variable. And of course, there's a non-negativity constraint because you cannot hire a negative number of apprentices. So the Lagrange can be written in this way. So there is this choice variable, and yeah, there's no inequality constraint either. So you can actually have no Lagrange. I'm sorry. So the problem will be simply like this. So the first order necessary condition will be given only in terms of only for the choice variable. So you have, so if you define this as profit of the master, so this profit is a function of labor. So the first derivative would look like this: a k alpha 1 minus alpha 1 plus L minus alpha minus W, right? Now, what do you know from the last week's discussion is that basically there are three cases, right? In one case, let me use green. In one case, there is this interior optimum, okay? Or in another case, let me use black. So there is this boundary optimum, but boundary optimum is still, does still have this derivative being equal to 0. Or using red now, I have this, okay? In that part, derivative will be negatively sloped, okay? So for this reason, we want this to be true, right? So the first condition will be this. The second condition, of course, I can put stars here. The second condition will look like that. 1 plus L star minus alpha W equal to 0. And finally, L star must be greater than or equal to 0. Now, how do you proceed from there? Be careful. You want to find L star as a function of the parameters and exogenous variables, right? So you want A here, K here, W here, and you can also write alpha explicitly. Okay, so what you want to do is to find this function that satisfies the first order conditions, and also the function should satisfy, of course, the second order sufficiency conditions as well, and we're going to check that as well. Okay, so here, of course, there are two cases. Case 1, L star could be 0, and case 2, L star could be strictly greater than 0. Okay, so we're gonna study both types of equilibrium. Okay, now I have a k to the alpha 1 minus alpha 1 plus L star to the minus alpha minus W less than or equal to 0, right? Now, if L star is equal to 0, this condition reduces into this one, right? I have A, K alpha, 1 minus alpha, less than W, right? Then I can understand that this does not violate the first of the necessary conditions, right? Because under this constraint, basically, if wage is sufficiently larger, okay, or alternatively, you can write the same inequality in this way. If productivity is sufficiently lower, right, sufficiently low, or if wage is sufficiently high, then L star equals 0 is, is satisfying the first of the necessary condition. Okay. Otherwise, I may have this 1 plus L star minus alpha less than or equal to 0 again. Now, if L star is greater than 0, the first order condition holds with strict equality, of course. Right? So then from this equation, of course, you can find L star. So it will be like 1 plus L star minus alpha equals W divided by 1 minus alpha A k to the alpha. So you have 1 plus L star equals 1 minus alpha A k to the alpha divided by W to the power of 1 over alpha. Okay, so finally, of course, you will have L star equals, there's someone writing check. Okay. So L star is 1 minus alpha A k to the alpha divided by wage to the power of 1 over alpha minus 1. Okay. Now, obviously, this is a candidate solution and it requires what? Now, if you imagine this way, so if this is your L star, L, let's say, is a function of productivity, okay? So what do I observe here? There is this particular level of productivity, let's call it a bar, okay? It's a threshold level. If productivity is lower than that, your choice of labor is 0. Okay, so this is 0. Okay. After that, it increases. Right? As you see, now this requires what? This number, since here L star must be greater than 0, right? So this number here this one should be greater than 1. But for this to be greater than 1, this should be greater than 1. This term inside the brackets, because 1 over alpha is positive, right? So for this to be greater than 1, you have 1 minus alpha times a, k to the alpha greater than w. In other words, a greater than a bar. Okay, that's it. So basically, you find L star as a piecewise function. Okay, L star as a function of a, k, w is a piecewise function. Okay, if it is 0, so it is 0 if a is less than or equal to a bar, and it is equal to the formula that we just found otherwise. Okay. Now the question is, of course, checking the second order sufficiency conditions. Okay. So remember the problem. I have profit. Profit is given in this way. Okay. And I want to check whether this function is what? I want to check what? Let me see. I want to check what?
Concavity.
Concavity, great. Because by theorem 2-2, if f is concave, then I'm good with the second order condition, right? So how to check the concavity for a one variable function? Basically, you look at the second derivative, right? So the first derivative was this. So it is a k alpha 1 minus alpha 1 plus L minus alpha w. So the second derivative is what? Minus alpha a k alpha 1 minus alpha 1 plus L minus alpha minus 1. Okay. Now, as you see, since alpha is between 0 and 1, and since L is non-negative, right? All these imply this is positive and this is negative. Okay. In fact, what we found here is that our objective function is strictly concave. Okay. So strict concavity also implies, as you know, the uniqueness of the solution. So that's it. So first of the condition, very simple, because this is a one variable problem. But importantly, you're gonna check both cases. Okay. Importantly, wait, there's a problem. I think there's a problem with my memory. Okay. So as you see, I still have 3 parts. Part 1, part 2, and part 3. Okay, all these should be satisfied by my solution candidates. Okay, and depending on where am I? Depending on parameters, okay, let's say in terms of productivity, we express the solution in this way. So from an economic point of view, of course, this is so meaningful if the workshop is not sufficiently productive. It is optimal for the master to work by himself or herself. Okay. You can also talk about capital stock. Okay, so you can write this condition in terms of capital stock, because that condition looks like this. Okay, that condition is basically A less than or equal to K alpha 1 minus alpha divided by wage, right? So you can write this differently, obviously. You can write this in this way. K alpha. Okay, wait. I think this is wrong. Wait, just a sec. Yes, sorry. It must be, so the condition is this, right? 1 minus alpha, k to the alpha. So this is your A bar, but alternatively, you can write this. K alpha less than or equal to this, and then k less than or equal to this. Then this becomes your threshold parameter for capital sub. So you can also tell me that if there is not enough tools, enough machines, enough material for the master and apprentice to work together by using them, if capital stock is small, then again the master would prefer to work by himself or herself. Okay, so you can express this condition in different ways, but from all points of view, since this is a very simple model of rational choice, and this is a well-behaved production function, and there's always positive profits for the master here, okay, for given wage, of course. Then there's a nice solution. Okay. So do you have any questions, comments, or anything to add about this? Again, it's very simple. We are just applying the procedure, right? Remember the procedure. Define your Lagrange. Here, there's no inequality constraint, so we don't have to define the Lagrange. We just basically work with the objective function itself. The first of the conditions, first we write the first of the conditions. Here, we have only one choice variable. We don't have inequality constraint. So with respect to the choice variable, we write the first of the conditions. Okay. These first of the conditions feature, of course, inequalities as well. And then there are two cases that could be optimal. One is L equal to 0. The other is L greater than 0, strictly greater than 0. So for both cases, we check and we see they can satisfy the first of the necessary conditions under different parameter values. So at the end, there is this one L star function, right? Your solution that satisfies your first order conditions. Then what you can do, what you should do, is to check the second order conditions. Since we have only one variable function, it's very easy to check the second order conditions, right? Because we basically look at the concavity of the function. So if the objective function is concave, then you got the solution, okay, by theorem 2.2. Okay. So let's look at another problem. Let's look at another problem. So imagine minimizing this function. Minimizing by choosing x alpha minus beta x, okay, transpose, I will explain, alpha minus beta x. So here, x is an n-dimensional vector, okay, and so let's assume it is just n-dimensional, so there is no non-negativity constraint, okay. So this basically means xi could be 0, it could be greater than 0, could be less than 0, or could be equal to 0, okay. Then alpha is another real vector of size, let's say, k, okay? And beta is another vector of size k, okay? So, sorry. So if this is k to 1, and if this is k to 1, we understand that this is okay, so they have okay, so it must be beta transpose, so it is so this is alpha transpose. So okay, alpha transpose, beta transpose. So this is 1 by k. This is 1 by k. And your x is k by, let's say, n. Well, for some reason, this didn't add up. Okay, forget about this problem. I will later on show a similar problem to you. Let's look at the firm problem. Let's imagine that there is a firm. This firm pays a rental cost, okay, for capital, plus pays for depreciation, okay? And this is the capital rented for this particular production process. Plus, there's a labor input, okay? So W is the wage that they have to pay. So in this problem, you have R delta W exogenous given greater than 0. Of course, delta should be between 0 and 1. Okay, so this is K and L. And suppose that you have a particular production target and the production function. Okay, FKL. Now, I told you before that minimizing a function, right, in a particular domain is maximizing this function in the same domain, right? So you can express your problem in the following way. Your Lagrange for this problem, this is your problem, and of course y is also given. This is your production target. Now your Lagrange is k l lambda, right? So you have minus r plus delta k WL, okay, plus lambda FKL minus Y, okay? So you refer to the conditions minus R plus delta, right? This is with respect to K. So minus R plus delta plus lambda Fk, right? Less than or equal to 0. Then K times minus R plus delta plus lambda Fk equals 0 and K greater than or equal to 0. Okay. Similarly, for L, you have what? You have minus W plus lambda FL less than or equal to 0. Then L times minus W plus lambda FL equal to 0. and L greater than 0. And finally, for the inequality constraint, you have, of course, f of KL minus y greater than or equal to 0, because your production must be at least equal to y. Then you have lambda times FKL minus y equals 0, and lambda greater than or equal to 0. Okay? Now you can solve this problem, of course, for many different production functions, right? So you may imagine your FKL is a simple Cobb-Douglas function. Okay. You can assume that this is the master-apprentice problem. Okay. Or you can also say that in this problem there can be automation. Okay. So suppose that this new variable, let's denote it by z. Okay. Now suppose that there are some robots, or there's a possibility of automating the production process. So instead of just master working by himself, there could be, if you make z greater than 1, you can basically say that this automation process is greater than 1 unit of work. Then, of course, you will ask, okay, but is automation free? Well, it doesn't have to be free, and in reality, it is not free. So you can extend, you can go back to the problem, and you may imagine that so there is a cost associated with automation as well. So first you have the regular capital stock, then you have labor, and then you have the automation capital, let's say, right? Then K, L, and Z are your choice variables. Okay, and your production function, of course, is now F, K, L, Z. All right. There are, of course, other fancier stuff. So imagine a production process like this one. Okay. So first, there are some tasks. Okay. Now for each task, you can use capital stock, okay, labor, or automation. And each task will be SCS, will obey a CS function. So rho here is between -infinity and 1. Okay, if rho is 1, the entire product, so these tasks, okay, so imagine that these tasks could be cognitive tasks, non-cognitive. Okay, they could be manual, they could be routine, etc. Okay, so for each task, you can use typical machines or tools, you can use human labor, or you can use automation systems. Okay, now rho determines the elasticity of substitution between the tasks, but within each task, they are perfectly substitutable. Okay, of course, that also depends on their productivities or production shares. All right, now of course your objective function is now a little bit different, because now you are paying R plus delta for all the capital stock you use. Then you are paying labor wage for all the labor you use, and you are paying P for all the automation materials, automation systems you are using. Okay? So your choice variables now are KI, LI, and ZI, where for each of them, I, of course, is between 0 and 1. Okay? And of course, once again, you have a production target. All right? So if, again, if rho is equal to 1, tasks are perfect substitutes. If rho is equal to minus infinity, tasks are perfect complements. If rho is going to 0, these tasks are units. The substitution elasticity is equal to 1 between the tasks. Okay, so all are same. Okay, as long as you understand solving this problem. Okay, as long as you understand how to solve this problem, then you can solve all these wild problems by using the same algorithms. Okay, now I have less than 3 minutes. Let me stop here for now before the break and answer your questions. I will give you more examples from different literatures. So entire microeconomic literature, I mean, right now you are taking micro as a must class as well, right? Most of you, I guess. So in that class, you will see several consumer problems. You will see several production problems. Okay. I'm fairly certain that you can solve all of these problems by using this methodology, because I've never seen in the entire micro sequence a choice problem where your choice variable can take negative values. All right, because either you are choosing prices if it's a monopoly problem, for instance, or a monopolistic competition problem, or you are choosing quantities. So in economics, thanks to our beautiful science, we have positive quantities and positive prices, or at least 0, right? So I do not enter some sector as a firm. I do not hire robotic capital as a firm. I do not consume a particular good because it is against my calorie constraint. Okay, things like that. So if you learn what I am teaching to you right now as an optimization theory, as a static optimization, there is no time, as you see, right? In a couple of weeks, we're gonna introduce. I mean, possibly this week we're gonna start working with the dynamic models. But if you learn the notion of nonlinear programming, if you practice it a lot, because there are several problems in your text, there are several problems in your micro texts. Okay, so once you learn that, you can be successful in any front. Okay, we have less than a minute. My time is 1:40. Is it okay if we meet at like 1:55 or something? Because video conversion takes around 10 minutes. All right, so I will see you in 1:55, and you think about your questions and anything that is unclear, so I can respond to them after the break. Okay. All right, I'm ending this right now.